So today I want to talk to you about two things. I want to talk about significant figures and also dimensional analysis and scientific notation, okay? So scientific notation, I'm going to do this because I've been noticing that a lot of us are having a tough time knowing how to write a number in scientific notation, okay? So scientific notation will always look like this, all right? Something like this, 3.2 times 10 to the, let's say, 8th power. All right, this number right here, 3.2, it's always, always, always between 1 and 10. So if it's 32, it's not, the number is not written in scientific notation. Okay, so it's between 1 and 10. And I will say this, it could be 1. So you could have exactly 1 times 10 to the 8th, okay? All right, now another thing is that 10 to the 8th, this exponent of 8, okay, is telling me that this is going to be a really, really big number. Okay, so if you have a positive exponent, you have a big number. If you have a big number and you want to write it in scientific notation, that is going to have to be a positive exponent. So I'm going to write that, okay? So positive exponent. And that means a big number. Now, big number could be, 10, 100, 1,000, and so on, okay? Another number in scientific notation could be something like this, 4.32 times 10 to the -6. All right, so that you're going to see either a positive exponent or a negative exponent, okay? And so if you realize it's got to be a big number, that kind of helps you to know, and you don't have to memorize, oh, if it's left, it's this, and if it's right, it's this, okay? It's like you understand that's a big number, so that's going to cause me that if I have a big number, like 930,000 in this next example, then that means you have to write that with a positive exponent, okay? So once again, 4.32, that's a number between 1 and 10. This negative exponent, in this case, it's going to give us a small number, okay? All right, so this first number, 930,000, we want to write it in scientific notation. Okay, so the number that we have to put, it has to be between 1 and 10, is going to have to be this 9.3 right here. So this would be written as 9.3 times 10 to the, okay, so there's a decimal place right here at the end of this last zero, okay, which means I would have to move it 1, 2, 3, 4, 5 places. Okay, so I need to move the decimal 5 places. And this is a big number, so this is going to have to be a positive exponent of 5. Okay, so 1, 2, 3, 4, 5. Big number, right? Big number, positive exponent. All right, let's go to the next one. I'm just going to slide it up. Okay, the 0.000036. So this is a small number, really, really small, okay? So that means I'm going to have a negative exponent. Okay, so the number that I'm going to write in front of my scientific notation is this 3. I have 36 here, but I'm going to write it as 3.6 times 10 raised to, I already know it's going to be negative. Now I just got to count the places, okay? So 1, 2, 3, 4, 5. So this would be an exponent of -5. So this would be 3.6 times 10 to the -5th. Okay? So this next problem, I'm asking you to take a number that's in scientific notation and write it in standard form. So write it as a decimal, okay? Now right here, this -4 right here, since that exponent's negative, that's telling me this is gonna have to be a small number. Small number. Okay, to make 2.5 to be a small number, I'm going to need to move the decimal to the left to make it small. So that's what tells me I need to move it left, is because I have a negative exponent and it's going to have to be small. Okay, so I'm going to write my 2, 5. Okay, the decimal was right here. I'm going to need to move it 4 places. So this is 1 place right now. Then I'm going to have to add a 0, and that would be now 2 places, 3 places, and 4 places, right? And so my decimal, if I move it 1, 2, 3, 4 right here. Okay, so I'm going to tell you something that I picked up on is when you have to move it left like this, okay, when you have to make it a smaller number, if you put a 0 on the left of this decimal, if you count the zeros, look how many zeros there are. There's 4, right? So that number right there, that -4, tells you you're gonna have to go left. And if you write 4 zeros and you put the decimal right after that first 0, then you will have the correct number, okay? Just one way, all right? Okay, this number, because it's a positive exponent, I know it's gonna be a big number. Big number. Okay. To create a big number of this, okay, I'd have to move the decimal 8 places. And which way to make the big number? Well, I'd have to move it to the right, okay? So this is 3 followed by a 4. Okay, so now that's 1 decimal place, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, and that's where my decimal place would be. And then I'm just going to go every 3 because that's hundreds, and then 1, 2, 3, and that's thousands. So this would be 340 million. That would be this number in scientific notation. Okay, or not in scientific notation. I said the wrong thing. In standard form. Okay, 3.4 times 10 to the 8th is 340 million. So big number, right? Okay, let's do the dimensional analysis next. So when we write these, okay, when we do this next problem, all right, I'm telling you, we have 458.3 terawatts, and I want to know how many watts that is, okay? So we're going to start with terawatts, and we're going to switch it to watts. Now notice something, we have watts here, right? And we have watts here. So this is a prefix, so that means you need to grab the prefix, metric prefixes that we have. Okay. Once again, all right, I want to go over this with you guys because a lot of us are not getting this. What this is telling us, okay, we had a tera, right? One tera is 10 to the 12th. A tera means 10 to the 12th. So 1 tera is 10 to the 12th of whatever, okay? So I need that. I need to use that because I know 1 terawatt, okay, is equal to 10 to the 12th, because that's what my chart said, watts. Okay, so the abbreviation for terawatt is 1 TW, capital T, capital W, is equal to 10 to the 12th, and the abbreviation for watts is a capital W. Okay, so we're just going to do dimensional analysis now, okay? So 458.3, we're going to start with that. 458.3 terawatts, so TW, times, okay, so I'm going to need the terawatts to be on the bottom. So that means 1 terawatt is going to go on the bottom. And 10 to the 12th watts is going to go on top. Okay, This terawatts is going to cancel with this terawatts. So I'm left with 458.3 times, times. Let me just put times 10 to the 12th watts. Now, if you multiply this out, it would give you the right answer. There's a problem with this though. It's not in scientific notation, okay? Plus, here's the other thing. We're multiplying, and this has four significant figures. Okay, this is what I talked about yesterday. 1 terawatt is exactly 10 to the 12th watts, okay? So this division right here has infinite sig figs. Okay, so we always look for the least, so we can actually even ignore that. We don't need those because those are exact. This is a rounded number right here. This is a measured value, okay? Now, I need 4 significant figures. I have that right here, okay? The only thing now is it's not in scientific notation. So I've got to move the decimal 2 places to the left, right, to make this, okay? So this would be 4.583. Now, I got to write this number in scientific notation. Now, this is a big number, so that means my exponent is positive. So times 10 to the, and how many places did I move it? I moved it 2 places. And then times 10 to the 12th watts. Well, now what do I do with these? I need to combine these two. Okay, so this would be 4.583 times 10 to the 14th watts. That's how many terawatts, or how many watts are in 458.3 terawatts. Okay, let's go to the next one. So this question is how many meters are in 4,362.5 feet. Okay, so that's what we're starting with. That's how many we have feet, and that's how many we have. We have 4,362.5 feet times, and what I want to do is I want to convert that to meters. All right. So if you look at your distance time conversions, okay, so distance time, that'd be this one. I see here that 1 foot is the same as 0.305 meters. Now this 1 foot is an exact value, but this 0.305 meters is an approximate value. So this has 3 significant figures, okay? So what I know is that 1 foot, let me write it right here. This is a conversion factor I'm going to need. 1 foot is equal to 0.305 meters. Okay, so 1 foot, 0.305 meters. Okay, and then this has 1, 2, 3, 4, 5 significant figures, whereas this number has 3 significant figures. So our answer is going to have the least number of significant figures, which in this case would be 3 right here, okay? Because we're multiplying by a number that has only 3 significant figures, okay? All right, so let me grab a calculator. I'm going to multiply. I wouldn't expect anybody to do that by hand, okay? So 4,000, I'll show you. 4,362.5 times 0.305, and you get 1,330.5625, okay? All right, so this is equivalent to 1,330.5625 meters, because this foot cancels with this foot. All right, now this number right here, we said had 1, 2, 3, 4, 5 significant figures. This number right here has 3, and this is an exact, so it has infinite. Okay, so the least is the 3. So this one has 3 significant figures. Okay, so that means our answer has to have only 3 significant figures. Okay, so here's my first one. Here's my second one. Here's my third one. All right, so I'm going to go 1, 2, 3. I need to use this fourth significant figure to know if I should round this third significant figure, and it's 0, so I'm not. So this turns out to be, in significant figures, the answer, as precise as the answer we can give is 1,330 meters. Now you could put a decimal here, all right, but you don't have to, okay? And this number right here has 3 significant figures. Okay, let's do a couple more examples. So this problem says how many microseconds, and that's mu s, okay, that's the Greek letter mu, in 4.35 days. So we're starting with that, okay, and we need to get to microseconds. That's the end. This is the start, this is the end. But to get to microseconds, I first have to have the root. So I need to get to seconds. So the idea behind this problem is I'm going to go from days, go to seconds, and then I'm going to go to microseconds. Okay, so days to seconds, if you get your distance time conversions, all right, we know 1 day is equal to 24 hours, or 24 hours. Okay, and then we know 1 hour is equal to 300 or 3,600 seconds. All right, and now we need to go from seconds to microseconds, which is a prefix, right? So micro. Okay, so 1 microsecond right here, 1 microsecond is equal to 10 to the -6 seconds. So 1 microsecond is equal to 10 to the -6 seconds. All right, so now we're ready. Okay, so we're gonna go 4.35 days times 1 day is 24 hour. Now I want to say something about this. 4.35 days, that's 3 significant figures. This 1 day and 24 hours, those are both exact. 1 day is defined as 24 hours. This has infinite significant figures, okay? So now we have hours, okay? And now we're gonna go hours to seconds. So 1 hour over 3,600 seconds. Okay, and then times, and then we're going to do seconds on the bottom, so that'd be 10 to the -6 seconds on the bottom, and 1 microsecond on top, mu of s, or not mu of s, mu s. Okay, all right, so this has 3 significant figures. So this one has 3 significant figures. This has infinite sig fig. That's this one. 1 hour is exactly 3,600 seconds, so that's infinite sig figs. And 1 over 10 to the -6, that's also exact, so that's infinite sig figs too. Okay, so what we're going to do is any 10 to a power, we're going to put by itself. We're going to separate it because that will become scientific notation, okay? So I'm going to multiply the 4.35 times the 24 times the 3600 all over 1, okay? So that would be equal to 4.35 times 24 times 3600, and then times, and what I have here is 1 over 10 to the negative 6 and microseconds. Okay, so I'm going to multiply this together. Grab my calculator. Okay, 4.35 times 24 times 3600. That gives me 375,000. So this is equal to 375,840 times 10 to the, okay, so 1 over 10 to the negative 6. That's from math class. 1 over 10 to the negative 6 is 10 to the 6th. So all of us should know that, okay? Because we've all had that math class that's taught that, okay? Microseconds. Okay, now here's the problem. This isn't in scientific notation. This needs to be a number between 1 and 10. So to make this number between 1 and 10, I'm going to have to move the decimal over here to just to the right of the 3, and this becomes 3.75840 times 10. Now that's a big number, so my exponent's going to have to be positive. So it's going to be 1, 2, 3, 4, 5 times 10 to the 5th times 10 to the 6th microseconds, okay? All right, so now we have 3.75840 times, and this becomes, you add these because here you're multiplying 5 of these 10s together, and here's 6, so that's 10 to the 11th power microseconds, okay? Now, now we're at the end, okay, and we have to do the correct number of significant figures, okay? So these all had infinite significant figures. This had 3 significant figures. So this number right here needs to be rounded to 3 significant figures. So I have 3, then the 7, and then the 5. That would be the 3rd significant figure. So I need to look at the 4th significant figure, right, 8. And that 8 tells me that's closer to 10, so I'm going to make this 5 become a 6, okay? So this is 3.76 times 10 to the 11th microseconds. And that's how you would do that problem, okay? So this one went from days to hours. This convert days to hours, and then hours to seconds, and then seconds to microseconds. All right, next problem. So for this one, we have 47.5 nanojoules, and the abbreviation for nanojoules is NJ, capital J for joules, is how many petajoules, okay? So the root word is joules. Now this is going to be different, okay, in that we have to go, we're going to start with this, we have this many nanojoules, so we're going to go nanojoules. But to go to petajoules, we first have to take kind of a detour, and we have to get to joules. And then from joules, we're going to have to take it and go to the petajoules. All right. So this is all prefixes. Okay. So what do we know? A nano. Okay. So 1 nano of something is equal to 10 to the negative 9th of that something. So that something in this case is joules. So 1 nanojoule is equivalent to, okay, so we're reading this, 1 nanojoule is equivalent to 10 to the negative 9th joules. So that'd be 10 to the negative 9th joules. Okay, how about petajoules? Okay, 1 petajoule is equal to 10 to the 15th joules. So 1 petajoule is equal to 10 to the 15th joules. So those are we're going to need those two conversions. Okay, we're going to start with 47.5 nanojoules. And then I'm going to multiply. So I'm going to get to joules. And the way I can get to joules is by using this conversion right here. So I'm going to put 1 nanojoule in the denominator, and that's 10 to the negative 9th joules. So my nanojoules cancel here. And then I'm going to multiply that by, okay, and I'm going to need to go from joules to petajoules. So here I'm going to do my conversion factor. And so I'm going to put 10 to the 15th joules in the bottom. And then 1 petajoule on top. Okay, so here I have a power 10 to a power, and here I have a 10 to a power. I want to put those as one fraction, okay? So this becomes, all right, 47.5. And I haven't been crossing them out, but here's nanojoules, and this nanojoules cancel, and this joules cancels. So I have 47.5 times 10 to the negative 9th over 10 to the 15th. So I want to keep these 10 to a powers together, okay? All right, so that'd be the same as what we have here, all right? And the exponent rules is 10 to the negative 9th over 10 to the 15th. Well, that'd be negative 9 minus 15. So this, and I should put, this is petajoules. So this would be equivalent to 47.5 times 10 to the, and then negative 9 minus 15 is negative 24 petajoules. All right, now we're not in scientific notation, okay? All right, so I need to move this. This is kind of a big number, 47.5. So I need to have a positive exponent, and I just need to move it one place. So this is 4.75 times 10 to the, and that needs to be a positive exponent. I only moved it once, so power of 1, and then times 10 to the negative 24th petajoules. And so now I'm going to add these exponents. So a 1 plus a negative 24 makes negative 23. So this is 4.75 times 10 to the negative 23 petajoules. Now, do we have the right number of significant figures? Okay. So right here, this 47.5, that has 3 significant figures. This 10 to the negative 9th joules is equal to 1 nanojoule. That is the definition, okay, of what a nano means, all right? So this is exact, and this 10 to the negative 9 exact, which means this has infinite significant figures. This 1 petajoule over 10 to the 15th joules, that's also by definition. A peta means 10 to the 15th of it, okay? So this also has infinite significant figures. So the one with the least amount of significant figures is this one, and we have 3. So our answer needs to have 3 significant figures, and lo and behold, we do. We have 3 significant figures right there. If it went more, okay, if we had more digits than these 3, then we would need to round if we needed to, okay? If it went out to like 4 decimal places. All right, so that's how you do dimensional analysis with multiplication and significant figures and just the whole shebang. This is it. I mean, this is really it. This is what I wanted you to learn the whole time, okay? And this is the exact thing why we had a tough time last week when I did that 1-4, okay? So everything should be coming together now for you.